Hello again. So we have seen that the spectrum can give us information about the temperature of a star or our star or of the surface of the star or of the parts of the atmosphere of the star. And you may wonder, how did we get this information that involves wavelength here? And how did this all occur? So we want to go back to what you learned about electron shells and the emitted photons so that you can understand that the light carries information. And what goes up must come down. So you know, and this is a really important point to make, that the photons can be absorbed in the electrons right around the nucleus, and in absorbing those photons, they can jump energy levels. And that is what goes up. Well, what goes up must come down, and a split second later, they emit those photon levels because they want to get back down to their equilibrium state. So in emitting those photon levels, they're emitting a very specific amount of energy. And the spectrograph detects that energy emission. And that energy emission, that amount of energy in those very unique electron shells for every element, that amount of energy is also unique and is picked up by the spectrograph in an emission. So what I wanted to show to you here is that when you have a very simple element like hydrogen, which is right at the top of the periodic table, very simple element, it has very few electron shells, and so it emits in very few places relatively. This is showing you the emissions in the visual part of the spectrum. And you're used to seeing the emissions with the ultraviolet and the purple over on the left. And I realize this is different, but it's a good slide that I think you can get used to the reversal. So when you have a simple element of hydrogen, you have very few electron shells in that element. So you have very few emissions in order to establish a pattern. Now, when you have a very complex element like uranium, which is way down here in the periodic chart, much more complex element, you have many more electron clouds and many more electron shells. And so now you have this very complex identification pattern to just your visual spectrum. And that emission spectroscopy detects only the discrete energy levels for your particular element. And this is showing the visual only. Let's take it a little bit more. The sun's spectrum, as it comes at you from the photosphere, contains over 90 elements. Now, we've talked about the fact that the most common elements go across the periodic table to iron, which is right here. But the sun also has up to 90 elements in it. The bigger elements, and it goes down to right around here. The bigger elements are not possible to be made by the sun, as we've discussed. The sun has over 100,000 of these lines because they have so many elements, and some of these elements have so many lines. So the sun's spectra, as it comes in, looks basically continuous because there's so many lines in there. I want to show you that when it comes to even the simplest element, hydrogen, there's some complexity there about what you see in these simple lines in red and blue and in purple. And what you're seeing here, and this is in your book as well, is you are seeing some energy clouds and energy shells that are telling you that there is higher energy in the emission here, and somewhat lower energy in the emission here. And those have a series. And that series tends to be around the nucleus of the hydrogen atom, and it's called the Balmer series. These are all the interpretation of electron shells, or if you want to call them clouds. And the Balmer series has very discrete, more like particles, in the way it drops down and gives you a discrete spectra line there. The visual spectra lines that you emit are called Balmer lines. Now, you see the visual. You don't see the ultraviolet because you can't see it. But this is an emission spectra that goes from ultraviolet all the way up to almost microwave. And you can do that on a spectrogram. And the Lyman lines are very close to very high energy waves. And so those lost a lot of energy. They came flying it down on an emission from the outermost electron shells. They lost a lot of energy, high energy emissions in ultraviolet. These infrared lines that you see here, these gray lines that don't have a color because they're not in the visual spectrum, they're in the infrared spectrum. Those lines are part of the Pasken's lines, and they don't have too far to go because, you know, infrared doesn't have that much energy. So I wanted you to connect the electron shells to the spectra, and this is the way it's done. Now, what you're seeing here is that now the spectra can tell you the temperature of an object, and it can identify the composition of an object. So you can say by the unique standard that you have, am I seeing helium coming from the sun? Or am I seeing hydrogen coming from the sun? Am I seeing some O2 in there? If you sent some light through water, you would have a unique spectra for the molecule of water. It's not an element now, it's a molecule. So it gets kind of complicated because now you've got hydrogen and you've got oxygen. And you not only got oxygen, but you've got oxygen. So you've got a more complex spectra. You could look for the spectra of methane, and certainly something you'd see in our atmosphere. And when you look through the spectra that goes through a solid, like light coming from a tungsten filament in a light bulb, or light coming through a prism, you can see that light filtering out for the elements of tungsten, or for the elements of the light before it went in through the prism. Let's go over that a little bit more. So in other words, you've got information in the light that talks about temperature and composition, and we can also have information in the light that talks about the velocity of the wave and the direction of the wave. So velocity is speed and direction. And you can tell both from this wave. It's an enormous treasure trove of information. We talked about the Doppler effect. You watched a video on the Doppler effect. Just to review very briefly. When the sound is coming at you, I drive an ambulance. When the sound is coming at a person at a stoplight, I always try to turn it down because it's so high pitched as it's coming toward the person. As it's moving away, I'm not worried because it's a lower pitch, right? So when we talk about that, we talk about a high energy wavelength, like a bluer wavelength. And when you're going away, we talk about a longer wavelength, like a redder wavelength. And so when an object is at rest and not moving anywhere, it is very true to its standard spectra, like the hydrogen that we just saw back there. It's standard spectra when it's at rest. And when it is moving, the colors of the spectra, especially in the visual, can move just a touch over. You wouldn't even see the difference of the color in your eyes, but the spectrograph can pick up the difference in the color. And it's called a blue shift if the star is coming toward you, or if the sample is coming toward you, or if the asteroid is coming toward you, or if the comet is coming toward you, or it's a red shift if those things are moving away. And we look at this to try to determine that the universe is still expanding and it's moving away from us, because we can see the Doppler shift and we can see the direction it's going as well. So if you want to look over radar detectors, same thing, Doppler. When we look at this Doppler shift, this is the way it looks. Here is your standard of regular hydrogen. Okay, your standard purple and blue. There's even a little bit of green and red. If you had a shift as though the sample of hydrogen was coming toward you, directly toward you, the star was coming toward you with all of its hydrogen, you would shift these lines to just a bit bluer, to just a bit more purple. You can't even see the difference with your eye, but a spectrograph can. It's called a blue shift. It's just moving the colors a little bit more blue. It doesn't mean that it looks more blue because you can't tell the difference, but a spectrograph can. If the source of the sample is moving away from you, you move a little bit more toward red. You move a red shift. You don't see a difference, the spectrograph does. And I think I'm going to stop it there because we're going to talk about the spectrograph next.